All right, I'm just going to get started. So real quick, this week we've been doing recruiting for our client projects. Does anyone have any questions regarding that? If any of you guys did apply? No? Let's just get started right away then. Oh, wait, I gotta record this. Okay, so, the first three lectures were kind of introduction to neural networks, deep learning, that kind of stuff, right? So if you remember, like the central purpose of why we brought up this idea of a neural network was so we could have a single, sorry, kind of the single blueprint, right? The single like algorithm that could learn any type of data, right? Now, of course, like, if you remember, a neural network has, consists of neurons. Neurons have their own individual weights and biases, right? So we're not expecting, hey, the same combination of weights and biases will work for any data set of data. We're not saying that. But we are saying this neural network, right? This algorithm, we can pick any set of weights and biases such that theoretically it could fit to any piece of data, like any data set, right? So that's a claim we made for those first three lectures. And thus far, I mean, we didn't have too many issues with that, right? So if you remember, we first brought up the perceptron. And so a perceptron is just a standalone neuron used for prediction. Perceptron is no better than your y equals mx plus b, right? Like if you only have a single input feature, your perceptron boils down to y equals mx plus b, right? But it's when you have these interconnected neurons, right? And each one of those having those nonlinear activation functions, the combination of those two elements allows you to learn really any arbitrary function. Note, I said it allows you to learn, makes you capable of learning. Not that you're guaranteed to learn the function you want to learn, right? So again, one of the examples we covered is a very simple housing data set, right? When you have three features, again, a feature is a type of input. So we have three features: size of a room, the number of bedrooms, and the age of a house, and we want to predict the sales price, right? And again, so far we've only been talking about like using a neural network on like this type of data set, like a tabular data set. Like we take a one-dimensional, array, and that's what we predict on, right? Again, when we train, all we're doing is we're just taking a bunch of these one-dimensional arrays and we're training those in batches or one at a time, right? And this is a constraint that we just kind of have to accept, right? Like neural networks, as they are now, only take a one-dimensional input, like a list of numbers, right? So what if we want to operate on images though, right? Images are at least two-dimensional, right? So on the right-hand side, or sorry, left-hand side, I have a grayscale image of a cat. So all that means is, for all images, one dimension is height, the other dimension is width. A single cell or a single pixel is a value ranging from 0 to 255. 0 meaning it's completely black, 255 meaning it's completely white, right? So again, a grayscale image has two dimensionals, height and width. Each cell contains the grayscale value. It's a single scalar, right? When we work with colored images, again, we have that height by width dimension, those first two dimensions. But then our third dimension is a tuple or a three-dimensional list. Sorry, not three-dimensional, a list of three elements that contains information about the red, green, and blue components of that pixel. RGB. If you guys have heard it from RGB, that's what it comes from. Red, green, blue, right? So for example, this pixel, right, has a red value of 91. Again, 0 being black, 255 being like it's completely red, or like a maxed out red value, right? So if you have, if your tuple of three numbers is 255, 255, 255, that means it's completely white. Whereas if it's like 000, that means it's completely black, right? Again, each of these elements tells you how red or how blue or how green that single pixel is, right? So again, with grayscale, our dimensions are we're working with a 2D input, height and width. With a colored or RGB image, we have three dimensions, the last one being the RGB value. Anyone have any questions about kind of the format of images? Great. Okay. So again, given some image, in this case, a grayscale image of a very low pixelated 5, right? How can we feed this into a neural network? Again, this is 2D, right? Our neural network can only take a one-dimensional list of data, right? So any guesses? It's not for now. It's not super complicated. Just you can, yeah,
Every pixel is an input.
yeah. So how would that be? Like right now, we could like how would you put every pixel as input? What do you mean by that?
Moving over and making it 1D.
Right. So yeah. I see. So each pixel will be its own independent feature. Exactly. Yeah, you're right. So we call that process flattening, right? There's a few different ways to flatten an image. The most, one conventional way is you split up your image into rows, right? And then you kind of rotate each row and then stack each row underneath one another, right? So again, we take that first row. That's our first set of, what is this? I think that's like maybe like 20 values, right? So the first 20 values of our neural network are from that first row. The 21 to 40th values are from the second row, and so on and so forth, right? So again, we call this flattening an image, taking something 2D to 1D. And again, we're not changing the pixel values at all. We're just kind of rearranging them to make them fit into a neural network. So again, this is totally possible, right? Like actually this handwriting data set is called MNIST, right? Um, like a neural network that was trained in this fashion was able to classify like the numbers 5 or 0 through 9, I think, fairly well. The problem is once you work with slightly more complicated pieces of data, like colored images or like larger grayscale images. So what this model of just flattening stuff out starts to like not work very well very quickly. Okay. So there's kind of two problems that comes with this, right? So the first is that images, unlike our tabular data, like our housing example, um, pixels are not independent of one another, right? So what that means is, again, in our housing example, right? It doesn't matter what this first feature is. Like I could take this bedroom feature, which is first, and swap it with the second one, or like move it twice. Like I can rearrange the order of the inputs. It does not matter. It does not impact the training of the model at all, right? Again, that isn't to say that like a neural network assumes the inputs are independence, right? Because obviously, like the more bedrooms you have, the square footage will increase, right? So those variables are related. That's just to say that the ordering of the features does not matter. The neural network does not care at all, right? But as you can see for images, I've kind of highlighted some features. The ordering of the pixels, like let's say you were just each feature or each pixel will be sent as a feature to a neural network, right? When you flatten, you completely lose that relationship, right? For example, like if you look at this box, right, you could say that, hey, all pixels in that region are inside the number 5, right? All pixels in this region, they're all part of the background. So the pixel's location in the picture matters, right? And again, like all pixels on this rough diagonal are from like form an edge, right? Again, when you flatten, right, like your neural network, you're hoping your neural network learns to like remember the relationships between the pixels. Like, hey, this pixel over here, this top pixel and that pixel, uh, I think they were adjacent to each other, right? So not only are you asking your neural network to like classify images, you're asking it to relearn lost data. So you're making it a lot harder for it. Right? So that's the first issue, right? Flattening loses spatial relationships. The second is more of a fundamental problem, like across all of machine learning, and it's called recursive dimensionality, right? So intuitively, it's fairly clear. So the more input features you have, right, the harder it is to train your model. And again, this is not just for neural networks. This is for all models, right? All optimization-based models, right? So the first two reasons are, fairly intuitive. A larger model, what does it mean to have a larger model? It means you have more neurons either widthwise or lengthwise, right? Regardless if you have more neurons, you have more parameters, weights and biases. If you have more weights and biases, that's more that's more steps in back propagation, right? That's more steps in feed forward. So training will be slower, right? Inference will be slower. More parameters also means you need to store more gradient intermediate values. Remember, when you're doing backprop in like say PyTorch or TensorFlow, it remembers all those intermediary values, all those gradients, right? So you could by having like a a massive neural network just crash your computer, right? But the fundamental issue, bigger than those first two, you could just have a really beefy computer, right? Just train on Ravana, UVA's compute servers. More fundamental issue is a large neural network is very, very prone to overfitting, right? So let's kind of walk through an example, right? So let's say we have a very simple, we want to like have a very simple model, right? Our only feature is sleep, and we want to predict a student's grade, right? Only one input feature. So let's say we train a linear regression model, or just, that effectively in this case means y equals mx plus b. Does anyone know what our two parameters are in this case? Cubes.
Your slope and your intercept.
Yes, a slope and intercept, m and b are only two parameters, right? And so again, like all things, remember when you have a neural network, when you're working with deep learning, your goal is to learn some function, right? So in this case, let's say hypothetically, this is a true relationship between the amount of sleep you get and what your grade is. I just made this up on the fly. Just let's assume that's the true relationship, right? You never have access to this true function, right? Because how would you? You can't ask every single student that ever existed. Even if you did, right, you'd have discrete values. Like this is a continuous function, right? What you normally do in the real world is you collect data from a data set. So in this case, I would interview, let's say in this case, only 4 students, ask them how much sleep they got, and then ask for their GPA, or like what percentage they got in like CS 1111, right? So again, our neural network, our model, whatever it is, or sorry, our regression model never sees this true relationship, but we want it to learn it, right? Okay. So again, if we just give our y equals mx plus b model these 4 data samples, well, we can expect it to do fairly well, right? I mean, you guys hopefully all took algebra one. Yeah, this is algebra one content, right? Like, just take 2 lines, right? And then calculate your M, calculate your B, right? Um, yeah, like there isn't too many ways to go wrong with this, right? Like, you could get unlucky and pick maybe these 2 middle numbers, but let's say you train multiple iterations of this. Like, assuming your training goes well, you will inevitably have a pretty nice line, right? Now, let's say hypothetically, we try to have a more expressive model, right? So this will be our stand-in for neural networks. Again, neural networks are kind of hard to visualize in this 1D example, right? So I call this the Vinny model. It was proposed by this man named Vainatya Rangaraju. He's a UVA alum, by the way. So what Vinny proposed is, it's a toy example, right? Let's say we want to learn like, a 2D relationship, like a function in terms of one variable, right? So grade sleep is a good example of this, right? um you basically have like a polyline, so to speak, right? So you take your line, add n breakpoints, right? And each breakpoint has 2 parameters, right? Your b, so effectively moving it up and down your y-axis, and then your m, which is effectively your slope, right? So again, similar to how a neural network, you can add as many neurons as you want, right? In the Vinny model, you can add as many breakpoints as you want, right? So for example, right? For this model with 6 corners, you'll have 12 parameters, and it'll look something like this. Does how this model work make sense? Okay, perfect. So again, let's try to use the Vinny model to, learn this y equals mx plus b, right? So again, naively, you could say, hey, this Vinny model is way more expressive than mx plus b, right? I mean, we could have as many, you could assume, hey, if we add as like 1,000 breakpoints, right? Or 1,000,000 breakpoints, we could learn effectively any 2D function we want, right? We could just add arbitrarily more breakpoints. So in the case, let's start small. Let's say we, start small. We only have 2 breakpoints, right? Just the 2 endpoints, right? Well, assuming we train our model, how we train doesn't matter. So assume training goes well, right? You could expect, let's say we randomly initialize the starting points, right? We'll have some variations, but they'll all look roughly the same, right? I mean, there's only 2 breakpoints. You're effectively moving 2 sides of the line. There's only so many ways you can move it while intersecting most of the points, right? So again, you would say that the Vinny model had fit to the data set very well, right? Because, if we look at each of our data points, they're very close to the line for every single of these variations. Does that make sense? So again, we would say it fit to our data set very well. Now, let's say we want to be extra, right? Like, let's say we want to try to make this better actually and add 6 breakpoints. Well, now we have a bit of an issue, right? Because each of these Vinny models that have 6 breakpoints, right? So again, breakpoints are the corners and endpoints. Um, they all intersect or get very like actually they intersect the points better than the 2 breakpoint model did, right? Like every single one of these points is being intersected. right? So again, we fit to the data set very well, but you can obviously very like visually, the model is kind of going crazy, right? It looks nothing like this true, nice, smooth relationship, right? So, you know, equivalently, like, using our lingo, like the training loss would be very, very low. It would be very low in this case. So what happens is with more parameters, we have more possible variations. We have a bunch of possible solutions, right? But again, because we have more variations, we have more of these whack solutions we don't want. Actually, most solutions will be whack solutions we don't want, right? I mean, there's so many ways to move this corner, for example, up and down. There's only like, the only optimal solution of moving this corner is like moving it in the middle. There are more whack solutions than good solutions, right? And fundamentally, this is what overfitting is, right? So this is why overfitting happens. You have more parameters than you do, or you have too many parameters, not enough data, and your model doesn't know how to like tune each of those parameters correctly. So again, in this case, the six breakpoint example, what's our solution? Just add more data points, right? So with 9 data points, we can't mess up, right? Like we just put the data points, or let's say we get lucky, sample some nice data points, and they fall in between those breakpoints. Assuming training goes well, we can't mess up this line, right? But again, let's say we didn't learn a lesson and add more breakpoints, right? Once again, we open ourselves up to more variations that fit the model very well, so it fits the data, but does not resemble the true relationship, right? And again, in the real world, right? Again, we don't have access to this true relationship. So how do we measure how badly we did? Does anyone know? Like, because again, our training loss is like very low for all of these examples. So how would we know in the real world when we're training our own models how badly we did? Yes, we have a separate train set and a separate test set, right? And the hope is that the test sets are effectively like, points that are on this true relationship. Um, yeah, like points on the true relationship that our model hasn't had the chance to overfit to. Okay. And so just to recap, this is what the cursive dimensionality is. It's more than just, hey, bigger model, harder, like, more computer trained. Fundamentally, it means that you need more data to avoid overfitting, right? So in the case of, trying to train our cat, or sorry, trying to train a neural network to identify a cat versus dog, like a classification task, right? Well, if it's 2048 by 2048, which is fairly high resolution, but a lot of images, like your iPhone is way higher resolution. Well, your first layer alone, right, will be forced to have, what is that? 41,000 or 4,001. What someone say it. I can't read. 1 million. What 1 million? Yeah, over 4 million parameters. Just your first layer alone, right? And probably more than that because you'll have biases, right? So, you're basically forced to have a very deep neural network, right? And you're effectively forcing yourself to overfits, right? No matter what you do, you will almost certainly overfit. Does that make sense? Does anyone have any questions about the cursive dimensionality? Okay. So again, that's why we don't just flatten any arbitrary image and chuck it through a neural network. What we do instead is use the titular convolution neural network. So the idea is, we still have our neural network portion, just as, these layers, we still have those, but we put them at the very end of the model, right? The beginning of the model, the portion that's in orange, the goal with these steps is to one, like learn some operation, some mechanism that captures these spatial relationships, right? Within our pixels. And then two, have a smaller inputs to feed into the neural network, right? So again, we're not like the goal is once we're at this first blue block, we're not sending the raw pixels into the neural network. We're feeding some other representation that's better than pixels, right? That they're smaller and we're hoping better represent the image than just raw pixels. Okay, so our first tool of doing that, our first operation is called the convolution. And so you're just applying, think of it as applying a filter to your base image, right? So again, your dimensions are mostly preserved. You're transforming an image, and intuitively you're highlighting things that, you're highlighting certain aspects of the image and hiding others. So for this first image, for example, you're highlighting kind of the edges, areas of like sharp contrast. And for the second example, you're highlighting specific textures that you want in the image, right? So how the operation works is you take some n by n matrix. In this case, I have a 3 by 3 matrix. And you, for each 3 by 3 window in your original image, you multiply your matrix, which is called your kernel, by that window, right? And so you do what's called element-wise matrix multiplication. So that minus 1 times the 0, that minus 1 times the 30, right? So you add all of those products up, and then the output of that first convolutional step takes up the pixel of your new image. So I was talking a lot. I'm going to like illustrate what I'm talking about, right? So the first step is the element-wise multiplication. Again, this is what we call a kernel. That's effectively our filter, right? By changing up the kernel, we'll have a different filter, like a filter effect, right? And so again, we start by taking the kernel and multiplying by the top right 3 by 3 piece of the image, right? Again, we're doing element-wise matrix multiplication, so the dimensions must match. Sorry. Again, it's minus 1 times 0, minus 1 times 30, minus 1 times 36, minus 1 times 49, 8 times 2, 38, right? Like the corresponding positions in both windows are being multiplied, and then we add them up. So in this case, we get a value of 146. So again, we're doing a transformation that doesn't really respect the idea of an image, right? So your output isn't exactly an image, right? So like this filter here, for example, like I changed the values so they fit between 0 and 255. But in reality, like this, like I had negatives in here, I had like really big numbers in here, right? Um, I just visualized it to, I just changed the numbers to make it easier to visualize. So after your convolution step, you no longer are working with images, you're just working with like multi-dimensional data. Okay. So again, like in this case, we just multiply by a specific window, but again, we're trying to output a whole nother, a whole nother end or ah, I don't want to say the word image because it's not an image, but a whole nother two-dimensional output. So we take that kernel and we slide it across our image. So again, we do our element-wise multiplication from the kernel with the top left, and that gives us 0. And then we do the same multiplication with the top right, and then we just keep moving that kernel across, right? And each time we get a new value, right? So this minus 66, that minus 66 will be in this position of the output image, right? So we keep sliding across, right? And then once we complete a row, we then move down, right? And so the amount that we move left or move down by is called a stride. So in this case, I slide the window by only like 1 pixel. So I have a stride of 1, right? Okay, so how do we pick these kernels? Well, in those cat images I showed earlier, I just manually picked them for like edge detection for feature emphasis. But in this, like the beauty of a CNN is that your kernel, you can think they're parameters, no different than your weights and biases. So this lets your CNN learn which filters it needs to use that are relevant for detecting your cat image, right? So maybe for detecting cats, the neural network on its own, the CNN on its own realizes, hey, I actually don't need to detect edges. I just need to get really good at highlighting where the cat's eyes are for some reason, right? Like generally the filters that the CNN learns and uses, they aren't really the most human interpretable. They are maybe in the first set of early layers, but the point is the filter is useful for the model, right? Okay, and just as I was saying earlier, the output of your convolutional step of sliding that kernel across your image is a whole new two-dimensional output. So again, this is not called an image. This is called a feature. And again, just for our sake for visualization, a scaled up feature maps outputs from 0 to 5. In reality, they are not constrained in that way. Yeah. So that's the convolutions. Does anyone have any questions about how this works? Yes. Yeah.
Did you say the results of all of those like multiplications are added up to the end?
Yeah. So for example, if we did a convolution like this top left convolution, right? So we multiply a kernel by this window of numbers. We add that. So actually, let me just move back to the, sorry. Yeah. So in this example, right? So we multiply each number of the kernel by the corresponding value in the actual image, and then we add those numbers up.
Okay.
And so that number is, sorry. Like that 146 is like
Oh, I see how it works.
in that location of the
Right,
output.
that makes sense. Okay.
Yeah. So again, like the product of multiplying the kernel by the window in this region that output is in the corresponding location of the larger feature map.
Right.
Can you expand kind of on what is like accomplished by this convolution? I think I get it, but
Yeah.
just expand.
Right. So what is going on? Like, why are we bothering doing this, right? So the goal of the convolution is to first like learn filters that the model thinks are useful for whatever task we have, right? So again, let's say like we want to classify something as a cat or not, right? Versus like a cat or a dog, right? Um like the goal of convolutions is highlighting certain parts of the image that identify what a cat is versus what's not a cat, right? So we'll talk about how we can use these outputs like to do that, but that's the point of convolution. It's highlighting aspects that we think are important or that the model thinks is important. Does that make sense? Okay. Later on we'll cover like how we use these feature maps. By the way, that's what the output of a convolution is. How we use these feature maps to actually, do classification, do these complex tasks. Okay. And again, just more terminology. Stride is the extent, as I said earlier, that we slide our window by. Slide in this case, or stride is, so it's a 2D vector. So the first index tells you how much you move it in the X direction. The second dimension tells you how you move it in the Y direction, right? Okay, so a stride of 1, 2, for example, means you moved like along the x-axis by 1 pixel, and you move along the y-axis by 2 pixels. So you on the y-axis, you're actually kind of skipping through stuff. There isn't as much overlap. Conventionally, your stride is like the x and y value is the same, like 1, 1, 2, 2, 3, 3, so on and so forth. Okay. And so adding is effectively adding like empty, like effectively placeholder values around the border of your image. And so what this does is it increases the size of the image. We'll talk a little bit more about why we do this in just a bit. But for now, generally before you do your convolution in your CNN, you might want to pad your picture up, right? Again, this increases the size of the output feature map. Okay, so again, just to reiterate, the convolutions output a feature map, and a feature map is just that 2D output that emphasizes aspects of the image that the model thinks might be important later down the line. Okay, so for example, let's say we do 64 convolutions in the same layer, or like we do 64 different convolutions at once. If we're training our model correctly, that means the model has 64 different ways of looking at the image or analyzing the image, right? Again, one convolution can like detect the whiskers of the cat. Another one could just like highlight the ear regions, right? A bunch of different ways to, just different ways of analyzing the model. Again, if you have too many convolutions, you could probably suspect that like a lot of convolutions will just end up being the same filter. The kernels will just look like the same thing. So just like with all things with machine learning, don't overfit, just control the number of convolutions you want to do in parallel. Okay. So question for you guys. Do you think the dimensions stay the same after you do a convolution, right? So in this example, like let's say your stride is 1 by 1, but you have no padding and a kernel size of 3 by 3. Do you think the dimensions stay the same after convolution? Any guesses? Smaller, yeah.
Maybe not, because you might lose some data due to the kernel, and like, you get like different values.
Right.
When you get right.
Yeah, so you think it might get a little bit smaller? Okay, I think when I just ask questions, I'll just have them be a binary. Like raise your hand if you think they'll get smaller.
Yeah.
Yeah. Raise your hand if you think they'll get bigger. All right, nice. I'm just gonna default to this from now on. Okay. So you were right. Dimensions do not always stay the same. They usually get smaller, right? So the bigger the stride, the smaller the image gets because you're skipping through more and more of the image, right? And again, the bigger your kernel is, like again, kernel filter, I'm using those interchangeably. The smaller your output feature map is. I want to say image, I mean the output, like the image. Okay, I meant the image of a function, but I can see how this is a little bit confusing. The smaller your output feature map is. And so the main reason why we use padding is to preserve the original dimensions of the image, right? So I know one of the things that we said about CNNs is like we want to reduce what we feed into the neural network. You could do that via convolutions, but generally we have a separate operation for that. So usually in the convolution steps, like we use padding to make sure the image does not get progressively smaller and smaller, right? So this is the formula for what your output size is going to look like. Again, you can see increasing the padding, increase the output size, increasing the filter size or increasing the stride decreases your output size. Okay. So we just covered convolutions, right? We have one more step though before we're done with those, which is the activation function, right? So another way of thinking of convolutions, or really your kernel, is they're effectively like the weights and your biases, right, of an image, right? So just like your weights and biases, they transform your data in a linear way, right? The weights are your slope, the bias is your intercept, moves it up and down. Similarly, a convolution is a linear operation. You're multiplying scalars by scalars and you add them up. Multiplication and addition. That's all linear relationships. So to learn more complex filters, you need to have a activation function at the end of your convolution step. So the activations are the exact same as you would have in your neural networks. So ReLU, for example, works perfectly well. The only difference, I guess, is that ReLU, these functions operate on individual pixels or individual cells. Convolution operates on like windows, right? Like ranges of pixels. Your activation function, just like before, only operates on individual cells, right? So convolutions transforms like groups of your image, whereas this operates on only a single pixel at a time. Any questions about how ReLU is used? It's still being used the same way. Learning nonlinear filters in this case. Okay. So right now we were just talking about like, okay, like we have original image and then we do a bunch of convolutions. We might do a bunch of them in parallel, but we're still just doing one layer of convolutions. Again, just like in a neural network, when you're working with convolutions, you generally stack your convolutions. So you do one convolution, you do like one set of convolutions, maybe in parallel, apply your activation function, and then feed them to another layer of convolutions, right? And so again, just like in a neural network, just having an activation function alone does not let you learn nonlinear functions. You need interconnected neurons, right? So this is the same kind of analogy, right? By having interconnected convolutional steps with nonlinear activation functions, you could learn more and more complex, or you're able to learn more and more complex filters, right? And you can imagine why like padding is very important in this case, because if you're doing all these convolutions, your image is going to end up shrinking unless you add padding before every convolution step, right? And again, the goal of convolutions is not to reduce the image size. The goal is to highlight important aspects of the image, right, that the model can use later on. So again, by stacking convolutions, all we're really doing though is like allowing us to, we're learning more complex filters, but we're not really able to associate large regions of the image, right? So like in our 3x3 filter, for example, we're only looking at the relation between like pixels in a very small, in a 3x3 window, right? In a very small window. In reality, when you look at an image, like if you're trying to tell if something's a cat or a dog, right? You don't just look at a small little frame of the image, you look at the whole thing at once, right? Now you might look at certain, like, might zoom in on the image to like look at texture, to look at specific features, but you also look at the global thing as well, right? So how do we kind of account for these global features? Well, one, we could naively just have really big kernels, right? Or a smarter way of doing this is by doing something called max pooling, right? So again, after we do our set of convolutions, max pooling is the next step. So what we do is we take our feature map, and again, we take a window, almost like you would in a convolution, but instead of doing some multiplication operation, you just take the biggest number in that window. So again, so think of that biggest number as a summary of that window, right? So again, the goal of max pooling is to take a window and quote unquote summarizing it, and just empirically it's shown that a decent summary is just taking the maximum value of a window, right? So unlike a convolution, you're not sliding your max pooling step across. You're just taking non-overlapping portions of the image. So is anyone curious as to why it wouldn't make sense to take overlapping parts of an image?
I don't have a question on that, but just out of curiosity,
Yeah.
like, does it ever make sense in max pooling to take like the mean or the average?
Yeah, in certain cases, people take the mean or the average. Yeah. This max pooling is again, max in the term means we take the largest number, but in some cases, you take the mean instead, right? To my understanding, it's just that taking the maximum is a cheaper operation, and it works just as well,
Okay.
right? Good question though. Yeah, and again, we're avoiding taking overlapping regions because again, unlike a convolution where we're trying to get as good of a fly or filter as we can, um, with a max pooling step, uh, we're trying to simplify our image. Like we're taking windows and we're trying to like condense them into a smaller representation. Yeah. One note in terms of implementation, with max pooling, like if your kernel isn't, or sorry, if your window isn't entirely divisible by the length or height, like for example, you have this little strip hanging off, you just chop it off, right? We just ignore that strip. Again, the whole point of max pooling is to reduce your image size, right? So, we start with a 28 by 28 image, for example. And if our max pooling window size is 3 by 3, we end up with a 9 by 9 image, right? Yeah, in this case, our stride. So to talk in terms of like CNN terms, our stride is equal to the pool size. If it's 3 by 3, we're sliding our window by 3 intervals or 3 pixel long intervals. And again, kind of to your question, this acts as a pretty decent summary, I'd say, of the original representation, right? This representation was a lot noisier. The max pooling almost had the effect of smoothing things over by taking the max pixel height. Okay. Again, as you can probably imagine, the larger your pool size is and the larger your stride is, the smaller your output becomes. Again, your stride does not have to be equal to the pool size. It just conventionally is. You can have it as big as you want, though. Okay. Again, I feel like I've been saying this a lot. The point of the max pooling step is to shrink that feature map. So later when you feed into the neural network, we're not sending it, the size of our original image, right? Okay. Yeah. And so the second big reason why we do this is to learn those global features, right? So now, right, again, we've reduced the dimensions of our image from 20 by 28 by like 9 by 9, right? Well, now we can just apply a 3 by 3 kernel and learn those global features, right? So does anyone know why would we, or does anyone want to try to take a guess? Um, why like do convolutions max pool and then do a set of convolutions instead of just having really large like kernel windows? Like why don't we just have, oh, sorry, instead of like, you know, reducing the dimensions or like really the resolution of the image by like 3, why don't we just multiply a kernel by 3? So have a 9 by 9 kernel to learn these global features. Right. Does anyone want to take a shot at it besides Shazam? All right, you got it.
So would it be like, would you be able to learn something you learned from the convolution first run and then as well as taking the features from the second one, the higher level features, and putting those two together?
Yeah, sort of, right? So your first set of convolutions before you max pool, those kind of detect like those filters, like assess the relationship between pixels that are nearby each other, right? Once you do your max pooling and you apply the same kernel, let's say the same 3 by 3 kernel, you can take a look at regions of the image that are originally farther apart, right? So I'm asking, why don't you just increase the kernel size? Why don't you just have a 9 by 9 or a 20 by 20 kernel? Like why bother max pooling?
Because then you don't have the same layers of complexity,
Close,
information.
sort of, right?
Has-
Not exactly, right? Because with large kernels, again, like the beyond shrinking your image, right? With a large kernel, we could still kind of look at how pixels that are far apart from each other interact, right? So I'm just gonna say it. A big reason why we bother with the max pooling step, besides trying to have a smaller neural network later down the line, is so we avoid overfitting. So we have fewer parameters, right? Again, by max pooling, we can have a 3x3 kernel function like very well instead of having a 9x9 kernel, right? Again, each number in that kernel has to be learned, is a parameter just like a weight and biases, right? So by max pooling, we get away with having a smaller kernel, right? So fewer parameters that work just as well as having a very large kernel with many parameters. Does that make sense? Cursive dimensionality. Okay. And so that's kind of it in terms of the orange region, right? So at this point, what do we have? We've taken our image, we've done a bunch of convolutions. Again, we're usually not doing one convolution each layer. We're doing multiple convolutions in parallel, right? So for example, we might have done like 64 convolutions in this first step, right? So we start by height times width, 2D, and then we start by whatever the dimensions are after a convolution times the number of convolutions we did. So it'd be height width by 64 if we did 64 convolutions, right? All our max pooling is doing is for each of those 64 dimensions or however many different feature maps we have, we're just shrinking it. So for example, we'd still have like 64 individual feature maps, but each one is very small. So we'd have like a 9x64, 9x9 feature maps. Okay, I have a visual kind of illustrating that a little bit later. Again, conventionally, when we talk about like a neural network embedded in another model, we refer to that components as the dense layer, right? And so again, this is more just terminology as opposed to like anything new conceptually. It's just layers of fully connected neurons, a neural network, right? So like I guess equivalently in a neural network, you would say that like, what's ever between the input layer and the output layer is your dense layer. So a neural network is just a dense layer, right? Okay, so again, after we do our convolution and max pooling steps, we have however many feature maps we have, but each feature map is fairly small. Does anyone remember how do we take these multiple feature maps and make them or restructure them in a way that a neural network can handle them? Does anyone remember?
Use convolution, then max pooling, then another convolution.
Yeah, so we've already done that, right? So right now in this case, we have like
So you
we flatten it out, right? So we have an n by n, we have 3 n by n images, right? So we flatten each of those. Well, I'll just show you, right? So we flatten each of those feature maps, each of those n by n images, and then we just stack each of those flattened feature maps together, right?
You mentioned at the beginning that one of the issues with like image analysis
Mhm.
with regular neural networks was you don't get like that spatial awareness between like pixel by pixel.
Yeah, good question.
Because you're flattening it.
Right.
You're still flattening the feature maps here. So how does that solve it?
Good question, right? So at this point, right? So these images are a little bit misleading. These are not images, right? These are not pixel values, right? So once you finish doing convolutions and your max pooling, you have this some n by n feature map that like encodes whatever relevant information you want, right? So again, like one set of feature maps, for example, might you might have end up with a 3x3 feature map where if all of like the values in that feature map are large, that means like the cat had whiskers, right? In other words, you end up with non-interpretable feature maps that don't really make much sense to us, but the model is basically crunched down that image into a way that it can better understand the image. Does that make sense? Like at this point, you're not working with pixels, right? Your convolutions kind of extracted all the spatial information it needed. The max pooling kind of summarized that spatial info. And what you're looking at right now is a summary of your image, if that makes sense. Again, if we look at it, it makes no sense to us, right? But it's a collection of like numbers that make sense to the model. That's like that the model can like feed into the neural network. Is that, I know it's kind of a rough answer. Does that make sense? Anyone have any questions about that?
How does this fix the problem of the space, like relative space to each other?
So how does this fix the problem of like, forgetting spatial features? Is that what you're at? Or spatial information?
Earlier, we were saying there's a problem if you have two pixels, it has to learn when the pixels are next to each other.
Mhm.
Just, is it the fact that it has less data points, just easier to learn that, or?
Yeah. So I guess my prior answer wasn't super clear. That's my bad. At this point, you don't really have pixels, right?
Yeah.
Each of these like two-dimensional arrays,
Mhm.
right? You can assume at this point that their order doesn't really matter,
Okay,
right? Like we've learned some structure, some representation in which these are no different than like if you were to flatten them out at this point. Does
It's
that
also
kind of
that,
make
like,
sense?
for each like feature in the feature map, right? Like for each feature map, it's already like a set of like a bunch of pixels have already been clumped together in like each pixel of the feature map. So it's like you're seeing that like it's pixel by pixel, but like each one of those pixels of like whatever, like the 16 by 16 thing is already a group of like 16 pixels in itself. So you're already getting that locality.
That's also a very good point, right? Like at this point, you've already like squished together all that spatial information, like condense it very down, right?
These are all like summaries of the feature map, and then the model's able to make, like, interpret them based on like learning the kernel earlier, like through what it was learning.
Yes,
So it all goes back to that.
exactly. It learns the kernel that kind of gives it the easiest representation to work with at this point. And again, I assume at this point, like, really, like you'd honestly go smaller than this. You'd probably end up with like a 3 by 3 or even like a 1 by 1, like a single scalar at this point, right? So again, if you have like 64 different feature maps, each feature map is like super small usually at this point. The feature map could just be a single scalar, which that number like either indicates like some aspect of the image. Like again, if that number is like 1, that means the cat had a tail or something, right? Does that kind of make sense?
So when it gets like that small, would that be like a sign of overfitting? Or is it
No,
just-
no.
just-
That means we kind of succeeded, right? If it gets well, that's more of a choice on your part as you develop the neural network. You'd only be concerned with overfitting if this model has to, like this dense layer has to get really big, right? But as I was saying earlier, like if you had like 64 feature maps, but each feature map is super small, then like for example, each feature map is only like 1 pixel big, sorry, not pixel, 1 cell, right? Then your neural network only has 64 inputs, right? Or if each feature map is 2 by 2 at this point, then you have 4 times 64 inputs. Still fairly small. Way smaller than the dimensions of the image, at least, the original image. Okay, again, at this point, we just flattened the image. And again, we're assuming that at this stage, like we've already extracted all the relevant spatial features. Flattening doesn't cause us to lose anything. Okay. So at this point, we've covered how to do the dense layer. Does anyone remember, like, if we're doing classification, right? What is our final activation function supposed to be? If we're doing classification.
Sigmoid.
Yes, for binary classification, it's sigmoid. Does anyone remember what it is for multi-class classification? Jubes. Softmax. Yeah, softmax is basically sigmoid, but for like a bunch of things, right? So again, traditionally, when you think of activation function, it operates on individual inputs or individual neurons. That's what the sigmoid does, right? It takes a single input. Softmax instead operates on the entire output layer, the entire set of outputs. And so you can think of these softmax, really, again, activation functions are used for two things. The first, most prevalent reason is to learn nonlinear relationships, right? The softmax isn't really doing that, right? It's not transforming the data in like a way we haven't seen before. All it's doing is scaling it such that our outputs, so again, in this case, let's say we're doing multi-class classification with 5 classes, right? All it's doing is for each class, it's outputting a probability. So the output of our softmax gives us, the outputs of the softmax search sum up to 1, and we have no negative values. Again, very nice, clean probabilities. So again, you could effectively as I said, I think maybe in last lecture, this is effectively an average, right? So if you ignore the E parts, you're just taking you're taking the value, right? And then you're dividing it by the sum of all the other values, right? So why do we bother with this E? Like, why do we have E raised to that value? Sorry, two reasons. The first, yeah. So the first is E to that power, guarantees a positive value. So like any number to like a negative number is still a positive number, right? The second reason, so but then okay, you could say, why don't I just sum up the absolute values, right? So the bigger reason of why we use the exponential, so E raised to some number, is that it exaggerates differences between values, right? So again, originally, for example, like 1.3 and 5.1, right? They're separated in terms of like a magnitude of 4, for example, right? But after we do our softmax, um, the 1.3 gets mapped to like 0.02, and that class 2 probability gets shot up to 0.9. So we're really exaggerating those differences. The third reason, I just forgot, is that unlike the absolute value, um, the exponential operation is continuous, right? Does anyone remember why? Sorry, they're both continuous. It's differentiable at all points, right? So the absolute value, remember, it looks like a V, right? With the corner at 0. And at that 0 point, it's not differentiable. Does anyone remember why do we care about, why does this need to be differentiable? Exactly, right? For back propagation, we need to calculate the gradients of every single step. Like that convolution, that max pooling, those are all actually differentiable, right? In this case, though, just taking the absolute value, that is not differentiable at a point, which runs the risk of screwing up our back propagation. Yeah, okay. 3 reasons why we do softmax. So this is just a summary. I know it's a lot of text. This is just everything we've talked about, right? So really quickly, convolutions, right? We start with applying a convolution to the base image. So small little kernels, right, applied to the entire big image. In that case, what we're doing is we're applying a filter that learns the relationships between nearby pixels. Right? Again, we're only looking at like a very small window. So we're just saying, hey, how do pixels in this 3x3 window interact? Right? We then transform those into a feature map, which is no longer an image. It's effectively a summary of the previous step. Right? And as we compound these convolutions, like we start summarizing that spatial data better and better. At some point, like we don't even like the spatial data is like completely summarized, right? So like the ordering of our elements doesn't really matter at that point, if that makes sense. Right? Unlike that of an image. Max pooling. So again, that fixes the first problem of, we want to learn spatial relationships in the image. Max pooling shrinks down our image. So one, right, we can get away with having a very small dense layer, a very small neural network at the end of our CNN. And two, it avoids us having to use really large kernels to learn like global relationships in the image, right? Okay. Right. So up until now, so really quickly, up until now, I've just been talking about grayscale, right? How do we deal with colored images, right? Well, we know how to do a convolution, maximum, all that on grayscale images, right? So we just, before we do our first convolution step, we just split our image into 3 channels, right? So again, we have our image consists of reds, greens, and blues, right? We just split them along those values, right? And then we do the convolution. So the same convolution, so remember it's the same convolution on each of these, or same set of convolutions, sorry, on each of these separate channels. And then we add up the results, and that's how we get our, our input to the next set of convolutions, right? So we just have this extra step at the beginning where we split into channels, we do convolutions, and then we add them back up. So yeah, so just make sure we keep track of dimensions, right? After that first step, we start with an image that's, some height by some width by 3 for 3 color channels. Assuming we, use padding correctly, we'll end up with each of our feature maps having the same height and width, but we'll have C number of feature maps, right? So if we did 64 convolutions, we'll have 64 feature maps, right? Okay. Yeah, that's pretty much it. So just some quick code at the end here. Um, again, this is all in PyTorch, right? So one of the first CNN architectures that was ever proposed was called VGGNet. Um, and so what they did is that yeah. So what they did is they took these convolutional blocks. So, they layered convolutions with ReLUs, convolution with ReLUs, and then a final max pooling step, right? So that's, we kind of stopped our CNN at this point, right? But what they decided to do is stack these blocks together, right? So at the end of the block, you can imagine, we have smaller, like at the end of each block, we end up with smaller and smaller feature maps, right? That get better and better at summarizing our output data, right? Okay, so for example, right, this first block, again, this is what we've been saying this whole time. The first block learns how adjacent pixels interact. Once we do that max pooling layer, we move on to that second block, we start learning how regions of the image that are farther apart start to interact, right? So again, the lower our resolution gets, the easier it is to like assess relationship between farther regions of our image. Yeah. So at this point, for example, okay, it's a little bit hard to see, but anywhere that there was like the cat's like we kind of highlighted the cat's general like body parts almost like its general facial features. Like again, anywhere where there's like an ear is lit up, anywhere where the nose is lit up, areas just dictating its fur are kind of like silence. So it's just highlighting like uh distinct parts of the cat. That sort of makes sense. And this is just one convolution, right? At this point, we might have like 100 different convolutions, right? This is just one example. Okay, so yeah, this is just illustrating that concept, right? First convolution, we're just looking at very narrowly how adjacent pixels interact. So generally, these first set of filters are learning like how to identify textures, things like that, right? These later convolutions are learning to like group together like objects or like like things in the image, so to speak, right? So again, like in this case, we can get the cat's entire ear in the same window. And the final set of convolutions is like grouping together separate objects, right? So in this case, we have the cat's ear and its entire face in the same window, right? As we move down these blocks, we assess like, we group together regions that were farther and farther apart. Okay, just to talk about a little bit in terms of syntax, right? So again, hopefully this PyTorch syntax is a bit of a review. With all PyTorch models, we must always import nn.module. That just gives us access to all these nice Python property or PyTorch properties. For example, as long as we nn.module, the class will start automatically tracking gradients, intermediate values when you do forward and back propagation. Like we don't have to code any of that. In terms of like creating this block structure, we use a sequential type. So all that's saying is like anything in this block like run sequentially. It's just a way of grouping together separate operations. So the convolution function in PyTorch, you start by inputting the number of input channels. So if we're working with an RGB image, we have 3 input channels. And then the second value is the number of kernels you want. So we can say, hey, we want 64 kernels for this first layer. Sorry, for this first sorry, for the first convolutional layer. You can detect the kernel size and the padding, right? So by having a kernel size of 3 and a padding of 1, we are making sure our image stays the same size, right? And then again, we have ReLU, more convolutions, so on and so forth. So yeah, and so we defined 5 different convolutional blocks. And then we can also define our dense block or our neural network component. So it's very important when really writing neural networks in general in PyTorch, but especially CNNs, is keeping track of your dimensions, right? So in this case, right, the after we do our flatten operation, so we've taken all of our feature maps, we flattened them into one-dimensional image. It's up to us to keep track of okay, how many separate inputs will our model now have, right? So you might notice that okay, like how do I keep track of stuff like that? Well, let me see if I can remember on the spot. Uh, All right, so after this step, you have 512 feature maps, each of size. Okay, I'm not even gonna remember how to. I don't remember like my progress. So it's very important to like keep a running tab on the dimensions of your image after each step. Because if you're like me and you try to like look at your final step, you're not gonna remember like how big your thing should be. So again, that first number takes the number of input features, like the size of your flattened vector. That second number is the number of neurons you want in that layer. And so from there, it's just a simple neural network. Yeah. And so this is kind of diagram illustrating the change in your dimensions. So again, you might start with a 24 by 24 image with 3 color channels, right? And then after each convolutional block, if you use a kernel size of 2, I believe, I think I was having, wait, 3, I don't know. I guess a kernel size of 2 in this case, you chop those dimensions in half, or sorry,
That's for cooling.
yeah, max pooling. Yeah, you got shoes. Yeah, the max pooling size is 2. That's why it's being chopped in half. Convolutions aren't changing the image size. So the max pooling step is chopping your dimensions in half, and this 512 comes from you choosing to have 512 separate convolutions at each step. Does that make sense? And so, you keep track, and that's how you end with that 7 times 7 times 512 number, which I don't know what that scalar value is, but that's what you end up. This is all mostly just review. So again, as always, I'll post this on the website. If you want to play around with some code, I think the VGGNet code specifically, you can check out this notebook I made last year. But otherwise, if you have any questions, stay behind. I appreciate you guys showing up.